What is... Daggy, I'm still recording. What is a theoretical physicist? Is it Sheldon from the Big Bang? Is it Einstein spouting off his ideas, lounging in a chair? Or is it a scientist running complex atomic simulations on a computer? Or could it even be a pre-med student running simulations on Newton's laws in a lab? Well, the short answer is yes. All of them are. Maybe not all of them are published physicists, but they're all physicists or theoretical physicists in a sense. Anyone who creates equations to describe the laws of physics, or anyone who uses those equations in computers and simulations, is a theoretical physicist. In that sense, there are theorists who create ideas, otherwise known as pen and paper physicists, like Sheldon from the Big Bang, and then there are theorists that apply those ideas in computers. And those are known as computational physicists. So let's start with an analogy. So there's the theoretical physicists, our pen and paper friends like Sheldon, and they theorize that an object balances on its center of mass. So in that sense, a child playing with a stack of objects and trying to balance them would be our experimental physicist. And a person doing the same thing in a video game would be a theoretical physicist. So the pen and paper theorist wrote down these laws of physics describing how it is that objects balance. So they both conducted experiments. The experimentalist, though, did one in the physical world, stacking objects, and then another one in the virtual world. That's our theoretical physicist. So, and let's say they both reach the same conclusion. That means that the theory works in both simulation and real life. So what separates the computational physicist from the experimentalist? Well, can't they do the same experiments? Kind of. The computational physicist is using fabricated data. It's like real fake data. It is data, but it is not data collected from the real world. The computational physicist can't test theories alone. Proving theories using computation would be like a snake eating its own tail. And what do I mean by that? Well, when computational physicists use software to run simulations, the simulations use the laws of physics as described by the programmer. So the programmer is the god of physics in their world when they write these laws. So if you write the wrong laws of physics, you will arrive at a wrong conclusion. So some of you may know that in games they'll reduce gravity to get better gameplay, so it's more fun. So imagine if someone said, I declare based on my new theory of gravity that gravity is actually half as strong as we said it was. Well, a simple experiment could prove this wacko wrong. But say that you ran a simulation using his theory, and then you prove that, wow, gravity really is half of what we thought it was before because of this wild new theory. But if you just drop an object and measure how long it takes to fall to the ground, you can see that that's clearly wrong with a simple experiment. So computationalists can't prove theories, but they can lend support to experiments and suggest new ideas. If we only use the previous examples, there's really not a need to run a simulation to prove that objects balance on their center of mass. We don't need a simulation to prove anything like that. What do we need that for? We need it for very tiny and small stuff, like atoms, molecules, stuff we can't capture on video with a microscope. Or we can simulate massive objects like solar systems. See what happens if, say, Jupiter was 3 times as massive as it was. Run a theoretical simulation like that. So let's take the tiny end. Let's go back there. The tiny, why would we want to run something so tiny? Well, let's say we have this crystal, a theoretical crystal. And an experimentalist runs experiments on it. They find all these properties of this crystal. But they might not know what it looks like up close on the inside. They might not know the structure of this crystal. They might not be able to figure it out. So this is where a computational physicist comes in handy. So the computational physicist will run a battery of tests and conclude, based on your experimental results, this structure is the only one that can produce these results. So using the results of a computational physicist, the experimentalist can say, okay, maybe I can understand a little better why something has the properties they do, and it can give ideas for new experiments. And crystal is just one example, but computational physics can help study cancer cells, viruses, and even the flow of water through our bodies. So in the end, computational physics is a branch of theoretical physics. Data is collected, but it's like I said before, it's real fake data. It's data that we can use and we can analyze it, but it's nothing that we can really use to support theories as much as a good experiment can, say. So you don't need to have new and exciting ideas necessarily, you just need to have an experimentalist buddy you can team up with and model their experiments and simulations. Or just find some old material no one's looked at in a long time and see if you can figure out what it looks like or what the charge distribution is and a whole bunch of other things. And because of advancements in computers, processors, graphics cards, computers in general, what physicists, chemists, and all scientists can simulate changes almost on a yearly basis. Thank you for watching. My name is Todd Lombardi, and I am a PhD student at the University of Missouri. I am currently researching in the field of computational physics myself.